Okay, so now I'm really pleased to introduce our second speaker of the morning. This is Alex Schwing, who's an assistant professor in the Department of Electrical and Computer Engineering at UIUC. Before that, he was at University of Toronto as a postdoc and did his PhD at ETH Zurich. I don't know if you know this or not, but each of you we sort of invited for a particular reason. Selected, targeted you in order to assemble the perfect group of people. In Alex's case, what led me to invite him was that he has a trajectory where he's worked or did a lot of work on probabilistic graphical models, which is something that I really understand well, and he's done more recently a lot of work in deep learning, which is something that I don't understand very well, and I think none of us do. And I think he's maybe one of the key people who might be able to bring connections between these two worlds for us and help us understand exactly what, if not today, then in general, of course, in your career, help us understand exactly what deep learning is and how to understand it. Thanks.
All right. Thanks so much, David, for this nice introduction. And thanks so much also for this perfect organization of this workshop and for inviting me. It has been really a pleasure being here and seeing all of those talks. It was really inspirational. And so I'm not going to talk much about graphical models today. I might also not talk too much about deep learning, actually. I'm kind of trying to look one step further. And I am kind of trying to show you what I'm excited about these days and what I think is kind of hopefully one of the next things that comes up. So now, as David mentioned, I did probably a lot in computer vision and machine learning. That's kind of the area where I'm doing my research in. And using the taxonomy that Jim kind of mentioned yesterday, I'm probably one of those folks that downloads data from the internet, and then we just try algorithms on those data, and we essentially develop algorithms. Now, one of those things that came out of the Toronto folks, one of those groups that is probably taking a similar approach, is kind of this entire deep learning hype, right? That many people are using these days, and we're using it because it generalizes what we were using so far, and it also works very well. To an extent that I'd probably almost say that deep learning essentially solves many of the prediction tasks that we are interested in these days. And if that is the case, assuming that we have obviously enough data and enough computational resources, but if that's the case, then the question is, what's kind of next? If we have solved, in quotation marks, prediction, what should we look at next? And just looking around here and listening to all those tasks yesterday, we don't have to look very far to figure out what are kind of the next things that we should be looking into, right? If I look at all those videos that were shown yesterday with kids playing around, exploring the world, being curious, being creative, producing somewhat consistent results, right? Computers are nothing like that. They are not at all curious, they're not at all creative, and maybe they produce somewhat consistent results, but even that fails occasionally. So the point I kind of want to make, and I summarize those as the 3 C's of cognitive computing, is that those are, according to my opinion, some of the next frontiers that we should be tackling. And to make that point, let me kind of tell you what exactly do I mean by that. And in order to do that, let's go on a small history of humankind. Very short history, very quickly. So just 10,000 years ago, right, our ancestors, we were essentially hunters. And we were using tools like spears to survive in the daily challenges. And eventually we started to settle down, helping each other, growing corn, domesticating animals, and refining all the tools that we are using in day-to-day challenges. And those tools became so powerful that eventually we were able to lift really heavy items and transport them across very long distances. Until eventually we started to connect all those tools together and transmit information very quickly. But what's next? In order to see what's next, let's look at what is common to what we have done so far. Well, what we've essentially done so far, what I would characterize as we have been using passive tools. Tools where we have to enable force in order to get to where we want to go, right? We have been using spares, we have been using plows, we have been using the steam engine or the computer. But importantly, in all those tools, you have to push a button in order to get to where you want to go, right? If I ask you to design a car, then you'd need to acquire a lot of knowledge and learn how to push a lot of buttons in order to get to where you want to go. And that's not at all efficient, right? We're using those tools to develop new technology, but that's a very time-consuming process at this time. It takes a lot of time to get there. So what I kind of think is the next frontier is, how about active tools? Tools that help us, in a sense, develop new technology almost automatically. And now you might be arguing, wait a second, that seems a little bit far-fetched. But actually, I don't think that's quite the case. If you look at companies like Boeing or Airbus, for example, what they're doing is they're designing parts for airplanes. Parts that are structurally very safe, but they are also very lightweight. And they don't use humans to do that. They have computer programs exploring tons of different structures, because they figured out humans just can't come up with those complicated structures anymore. Computers are much more effective at doing that. And they refer to that as bionic or generative design. And that's, in a sense, something that we just heard in the talk earlier, which is why I'm happy kind of talking right after your talk, because it's this mentality of generating new things, coming up with new things, right? Just like generating those pictures. And in fact, we can use similar tools like those to design novel drugs or to summarize text. It's pretty much the same task, to describe a scene or to colorize an image. Now, what do all those tasks have in common? Well, all those tasks have in common that there is not a single solution that fits well, right? If I give you a text and ask you to summarize the text, every single one of you will come back with a text that is different. And there's not a better one or a worse one, right? They're different for some reason, and that's fine, and that's all good. If I would ask you to summarize the text in 50 words, I'd impose a constraint. But nonetheless, the text would still be different. And if I would ask you to summarize it in 50 words using 3 distinct words that I gave to you, it would still be different. So there's just so many constraints. And nonetheless, all of those solutions are somewhat equal. And I think those are the interesting tasks that that we have to look at. And in this area here, I see many tasks as well that fit into this egocentric vision framework, right? I just have to look at the website, and that's what I did for this workshop. And the first task that comes up there is video summarization, right? Just like text summarization, there is not a single video or textual description that summarizes the video. There's plenty of solutions out there.
So you work with probabilistic graphical models. Those models predict probability distributions, which is exactly what you just described.
Well, so in probabilistic graphical models, we are characterizing a probabilistic distribution. That's right. But what we are often doing is we're going for the map solution, the maximum a posteriori solution, which is the highest scoring configuration. And later on, I'll refer to those, exactly those points later. What we want to do is we want to characterize multiple different solutions. The problem is that this is a computationally very hard task. And it's a very good point. I'll have a slide later on where I'm exactly pointing those things out. I'll get back to you on that, but very great, very good point. And then there's plenty of other tasks, understanding of social salience, activity analysis, human interaction recognition, focus of attention modeling. All those are tasks where there is often not a single viable solution. There's multiple solutions, and they are all equally good. And kind of to make this point, as humans, oftentimes we're not thinking about a single solution or trying to predict a single solution. We're envisioning what's going to happen if we're analyzing. We are coming up with different scenarios, and then we're assessing those scenarios. But I'd argue that computers at this point in time, they're not very much like that. So to kind of drive home this point, what we need is algorithms that explore the space of solutions, all possible solutions, and are somewhat curious, or I would refer to that as curiosity. But they shouldn't just explore that exhaustively, right? We want them to come up with some creative solutions as well. But as I mentioned earlier, we also want them to take into account constraints. Constraints like summarize the text in 50 words. Or kind of put the other way around in mathematics. I'm just now going from the other side backwards. So what do I mean by curiosity, creativity, and consistency? Well, exploring all possible solutions and the need for effective mechanisms to produce diverse solutions as outputs, and producing solutions that are globally coherent. Now, let me show you 4 vignettes of the type of work that we have been doing at UIUC that I'd characterize that fit into this category to really make this more concrete. And I'll start with showing some recent work that I put into this category of curiosity and creativity. What we did was we took images and we asked the computer to generate questions that fit the observed scene. But not only was the computer required to generate a single question, it was required to generate a whole set of questions that match. Then I talk a little bit about video object segmentation, and I think that could be of great interest to many of you here as well. And also attention mechanisms is something that we have been looking into. And I show kind of how we look at that from a deep learning point of view, maybe. And then, if time permits, I'll talk a little bit about graphical models at the very end, where we model structured output spaces for like those generative techniques. All right, and now before I jump in, I guess the point that I should make, all this work has been done in collaboration with an amazing set of students, and really the credit goes to the students. So they are really the magicians that made all this happen, as opposed to myself. I guess I just get to talk about it. So the first, what's that?
Are you APS?
Yes, that's, I try to shorten my name. That's right. Otherwise it wouldn't fit. So yeah, here in this case, that was work done by Unad and Siv. And they are, so we titled this Creativity Generating Diverse Questions Using Variation Autoencoders, and that's work that's going to appear at this year's CVPR, I guess in 2 months from now, or a little less than that. That's the Computer Vision and Pattern Recognition Conference.
How many thousand people? 3,000. It's the most important conference this year.
But it's, I'm not going to weigh in whether it's the most important one. It is a very important conference in the area that I've worked in. That's for sure. So what was kind of the task that we looked at here? So given a single input image, what we wanted, like the one that I'm showing you here on the left-hand side, we want the computer to come up with a question that sticks or kind of fits to the scene that is observed. But what you would obtain if you were to train like standard deep learning systems is you would obtain a system where you feed in the image, you get a question. You feed in the image again, you get the same question. And irrespective of whether that question would fit or not fit, you would always get the same output. And what we want to do here is we want to do something that is slightly different. As I mentioned earlier, we want to feed in the image and get an output, feed in the image again, and get some different output. And that output should still fit the scene. So what we're doing here, as I said, generating questions. And if you look at the questions that the system generates, is there a candle burning? How many people are in the room? Is this a formal occasion? They all kind of fit the scene that is observed here.
You also get data from human observers doing exactly the same task.
We do have ground truth data and data from human observers, so I'll evaluate that a little later on down the road. But yes, good question. We do have data because we need to. It's a learning-based system, so we have to train this system. So we actually have a lot of data, like a lot. And so as I pointed out, we want to generate questions that, on the one hand, reflect the content of the scene, but we also want to make sure that we generate diverse and creative questions. Now that comes back to your point. How would we do that? Well, the classical way of doing that would probably be, okay, you take your image, you extract some form of representation, some features, and then you form an energy function over questions, probably some probabilistic graphical model, and then you have two options. Option number one, you extract the highest scoring configurations, the highest scoring questions. That may work. The problem with that approach is that you'd often see very similar questions. And the reason is that you just change a word here and there, and the energy doesn't change very much. The probability doesn't change very much. So that's probably not exactly what we want. Then you could argue, okay, well, if that's not what we want, then how about I extract the modes of my probability distribution? Okay, you could go for that. The problem is, in high-dimensional probability spaces, that's computationally very expensive to do. And we want techniques where you feed in the image and you get an output like almost instantly. Could we come up with systems like that? So that's kind of the question that we were asking ourselves. And to the rescue comes one of the techniques that has been proposed recently, which is known as variational autoencoders. So at a high level, what we are doing is we're taking during training the image or its representation and an input training sentence or question, and then we're encoding that in some probability space, some manifold space. And then during testing, we're taking a sample from this manifold space plus the image representation, and then we're decoding it to come up with the question. Now, the point I should make here as well is that the questions that I showed you earlier, and I will show you in a bit, are all generated word by word. Similar to what Ruslan Salakudinov was mentioning in his talk yesterday, those language models that we're able to train these days are reasonably good at generating text that is reasonably coherent. And we'll observe exactly the same thing here, particularly for questions that are not as long as the text that Ruslan has been showing us.
In human modeling, it's very common to select outputs in proportion to the probabilities of the student. And this seems like, I wonder if that's worth trying. This is a fairly complicated point.
We actually model probability distributions, and you'll see that the decoder comes up with a probability distribution, and then we will take the highest scoring probability from there. So
what I'm saying is that in human model, we often output samples in proportion to probabilities.
So that would be like you're trying to sample, which you could probably do as well. I think if you do that, again, because you're trying to model a very high-dimensional space, sampling is a very inefficient technique to explore high-dimensional spaces. And this approach is really very simple. During inference, it's really just a forward pass in a neural network, and you have your output. So that is, it can't get more efficient than that. And to differentiate that from existing techniques, what we're doing is we're, instead of sampling at the output space, we're kind of sampling at an input space, and then we're transforming that learned probability distribution through a neural net to match what we want to get at. So the difference is, in a sense, sample at the input space and then go to the output via a deterministic computation, as opposed to sampling at the output space.
And that's very common in human modeling as well. Sometimes the noise at the beginning or at the end is simple.
Right, yeah, very good point. And that's exactly what we've been doing here. So kind of to summarize, we extract image representations, we learn an encoding, and then we generate by decoding. And as I mentioned earlier, this is reminiscent of those variational autoencoder techniques that have been proposed not too long ago. Now, the two important tools here are the encoder and the decoder, right? So what do those look like? So in this case, we use, and Ruslan has been talking about that yesterday as well, we use what is referred to as these long short-term memory networks. What it does is it takes an image representation, think of that as a vector, kind of encodes that into some latent or intermediate space, and then it also takes the words or the words of the question as input, embeds them linearly, and then uses those vector representations and kind of propagates that forward, where in those LSTM units there is some memory cells, so it tries to keep some states in mind until eventually we end up with a latent or hidden representation. that is then used to encode this probability space. And in fact, the decoder looks very similar. The only difference is that we now have this additional sample that comes in from this probability space. And this was the design that we opted for in experiments that seemed to be the design that worked best in our case for this particular task. And here, this is where the different questions get, in a sense, generated, right? Because those samples differ depending on depending on when you throw the sample at your computer, when you throw the image at your computer. And this is when the different questions get generated. And again, coming back to, I guess, your comment, here we obtain then probability distributions over a vocabulary of words, and then we really generate the question word by word, like one step after the other. So here you can kind of think of that this is think of it as a time sequence, and you're stepping through this model one step at a time. So you start with a start word, and then you generate the first word, you plug the first word in, you generate the second word, and you kind of keep stepping through that until eventually you generate like an end symbol, and this is when the generation process stops. So we trained the whole thing. These architectures are, you can backpropagate through them end to end. Everything is differentiable, so we can train the parameters, and that happens via maximizing a lower bound on the log likelihood. I'll spare you with all the math. I hope you trust that we did do that reasonably well. We used VGGNet image representations. VGGNet is a specific neural net from folks at Oxford. And one of the important things in order to make this work was there is this traditional data set, the VQG data set for visual question generation data set. And that data set probably contains 15,000 samples. So we first tried it on this VQG data set, and what we realized immediately was that data set is just not rich enough. Luckily, there is what is called the visual question answering data set, which also contains images and questions. So we had to leverage, which is also significantly bigger, and we had to leverage the combination of both in order to make this, this system do something reasonable. And the combination of both is probably like 500,000 training examples. So some reasonable amount of data that we had to take advantage of here.
One question, what was the loss?
The loss was a standard cross-entropy loss. I think I had it somewhere here, actually. This is the standard log loss, cross-entropy loss. Then for matching this distribution, we had a standard KL loss. Yeah, I should have mentioned that earlier. Sorry. So here are then a couple of results that I can show you. There's a bunch of images, and you can see, for example, there's a mountain biker here, and it's asking questions like, is this man wearing a helmet? Or what kind of bike is this man riding? And then if you show it a different question, say this train here, it's not asking anything about a helmet or a bike. It's kind of asking, is this train in a rural setting? Or is this train in the United States? It asks those type of questions. Now with tick mark, I kind of highlighted those sentences that it has never ever seen before in the training set anywhere. To kind of illustrate that system is not only capable of reciting questions that appeared somewhere in the training set, but it's actually generating new questions that had never ever appeared before.
One is the cat getting ready to see.
Oh, this one? Yeah.
Yeah, like if that's allowable, then couldn't it be anything? Like, is the cat purple? Is the cat, and you just say anything, you know, is the cat Martian? Is the cat, you know, brilliant? Just add any words after is the cat.
Right. It could do anything of that form, but it couldn't ask a question of, is the man wearing a helmet, right? That would not fit in this context.
Yeah, but
so it has to
ask the question that just is the cat the. Why is that useful?
And that's a very good point that kind of brings me to one of the things that we are looking into right now is at this point in time, the questions that we generate are not controllable in a sense that we feed in an image and it comes up with questions. But we have no mechanism that allows us to control what should the question focus on. And that's something that we have now done in follow-up work, which I didn't or haven't put onto slides here. which we just submitted to a conference like 1 or 2 weeks ago, which is kind of how can we make this mechanism controllable such that we can kind of steer. We want to generate diverse questions, but the question should focus on one specific aspect in the image.
So this is sort of interesting because humans, the data set is generated by humans. Right. And they are picking questions that are based on their knowledge, their whole history of knowledge, and what they think the viewer might want to know. You know, it's sort of like what's interesting.
Right.
And you're training on that, but somehow it's not picking up those aspects. And it is maybe somehow a little bit, but it's sort of randomly mixing and matching, so it's not really picking up those aspects too.
Right, it does pick up a few aspects, and I later on show some failure cases, and you will clearly see that it does pick up some of the statistics inside the training sets. And sometimes that's good, but sometimes that clearly goes wrong, and I show some failure cases where it does go wrong.
You might want to comment on to what extent is there a model of a question built into this? Because the question is the thing we understand, right, as humans. And you might describe like what extent are questions being modeled and how are they being modeled?
Right, so I guess that goes back to those two architectures, the encoder and the decoder that I showed, and there are parameters in those two neural nets, and they are trying to model the questions and what is like the structure within a question, and so we are trying to learn this automatically from the data set without kind of encoding that explicitly.
But for example, there's no grammar. So
No.
Know what it means to develop one question.
Right, exactly.
There's some kind of word statistics, and then there's a question about like what is the temporal kind of dependency structure? You know, to what extent are you modeling? You know, so sentence at the end of the question mark, and then there has to be things that come before the question mark that make sense, and then to what extent is the sentence actually guaranteed to sort of have that property?
Right. So we don't put anything of that form in there. So that is extracted purely from the data set. And
one last point, and the answers to these questions so far are yes or no, or sometimes a number. What's the space of answers? So it's the space of questions, right? So what's the space of allowable answers that's defined by the space of question for learning?
So again, here we also did not restrict the type of questions. So the answers can be just yes, no.
It's mostly yes, no.
For this data set that we used, there is a significant bias. So I think 70% of the questions are yes, no, if I remember that correctly. There's a new data set coming up, and in that data set, that bias is kind of alleviated a little bit. So we'll be using that data set going forward. But the data sets that existed so far did have a significant bias in that. That's true. And I show some statistics later on as well, and we'll see that there is some bias that it also latches on. And I guess, yeah, speaking about the failure cases, things that are kind of hard to extract. So here on the left-hand side, you see kind of a strange-looking plane, and it asks about multiple planes flying in formation, right? That doesn't quite make sense here. And that's something it probably has never seen trains like that during training, which is why it doesn't exactly know what to do. But then coming back to the bias, there in the background, you can kind of see a hot dog, and it's asking what is the green vegetable on the plate. But there is no green vegetable on the plate. And the reason to ask for green vegetable is because if you mine the data sets, you see plenty of food items where there is green items, and the people that we asked to generate that were asked to generate the questions, they are kind of always asking about the greens. So there's a significant bias in the data set, and obviously during training, then it picks up this bias, which is good or bad, right? On the one hand side, we don't want that to happen, but on the other side, that's the data that we feed into the networks. So they are obviously picking up those biases.
And I guess the other point would be this one about the meat on the hot dog, where on is just the wrong word.
Right.
And it gets back to this notion that there's no grammar really there.
Right. Yeah, there's a few other sentences. If I would have gone back, there's some sentences where sometimes it picks up or it uses some wrong words in there. I guess we still, as humans, we still figure out what the model wants to do, but sometimes it's just not exactly consistent. And that brings me back to what I mentioned earlier. It's not only important to have creativity, but we also want to go for consistency, which is something that and may or probably may not have the chance to talk much about.
It's picking on because a lot of the questions are about spatial relations in the data set.
Yeah, there are a lot of questions about on. What's
Right.
on the plate? What's
Right. Yeah, that's true. And so we have some quantitative analysis. I'm not exactly sure. I may be running short on time, so I quickly skip through those. What we're showing here is on the x-axis, you can see over the training iterations, on the y-axis, some evaluation metric, and the black line is a baseline that people came up with before we looked into this problem. And on this metric, the method that I just showed to you does reasonably well, which I'm very happy for the students. So that's great. We also looked at other metrics. So there's, I guess, Bleu and Meteor are two kind of metrics that are used in that field, and that probably also goes back to your question, like evaluating on a test data set, not only generating questions but really assessing the quality of the questions. So those are two metrics. It's they look at the question and the consistency of the question and whether the question fits to some reference. What's that?
Who does the judgment?
Oh, those are two metrics, like accuracy, or it's just it's a formula which allows you to kind of compute does the question.
Is that a human judgment?
So there's a reference question, or there's a set of reference questions, and a set of reference questions, and then it compares the generated question to that set of reference questions. And right, exactly, it's an automated way of assessing the quality. Yeah, in many of the cases we are using automated ways of assessing the quality. And we also looked at the generative strength, and again, here we kind of plotting the unique questions that it generates per image, and you can kind of see over the training iterations, the counts kind of keep increasing, which is something encouraging. Or probably more interesting is what we call the inventiveness, the unique unseen questions per total unique questions that it generates. And again, there's a decent fraction of questions that it has never ever seen before that it kind of comes up with and generates. And so that's kind of nice. So looking also a little bit at the diversity here, you can kind of see what type of questions is it that it generates. And you can see here there are those rings, right? The inner ring is kind of the first word that it generates. So there's a significant amount of what questions, is questions, how and are questions. And then for the second word, what is the name of is kind of a very frequent question, for example. And those are the different data sets that we evaluated on. Now, the nice thing is I should have probably plotted the scores on the for the training set as well. Those plots look very similar to the metrics that we obtained from the training set. And so that goes back to capturing the biases in the training set, which I think is a good thing. That's what we wanted to do in a sense. Okay, so now that brings me kind of to the second part that I wanted to look into, which is visual question answering attention modules for multiple data modalities, which in this case is work that was done by Idan and Tamir. And again, really credit goes to them. So
sorry, I have to interrupt you.
Sure.
Which thing really bothers me? What is that?
Oh, those are the magicians that did the work.
Sorry. It's totally fine.
Oh, I see. Yeah, I think I said that earlier. The magicians are kind of those. But
See that.
I see. Yeah, maybe I should pick a. I see. Maybe I should pick a better one. Yeah, my bad. Is it okay? I should pick a magician next time. I just figured it looks kind of cute. Anyway, point being, visual question answering. So what's the task? The task is, given an image, now we're not generating a question anymore. We want to go one step further. Suppose we have an image and we have the corresponding question. We want to generate, or we want to answer that question. We have the computer to be able to answer that question. So here's an example, and two questions that could fit or that were assigned to this question, to this image is how many people are watching The Man, or what game is this? Now, importantly, what we are interested in is we don't want to just answer that question. We want the algorithm to focus, like a human does, focus on specific parts of the image, right? if there is how many people are watching the man, then I don't care much about the man. I care more about what is happening in the background, as opposed to what game is this, where I probably look at the man in the foreground, right? And we want systems like deep learning systems that do similar things. So here is an attention mechanism that we designed, and what it does is it kind of, depending on the image and the question, it comes up with focal points in the image from where it extracts the information that seems to be useful to answer this question. Now, the important thing I should point out here is we trained those systems without providing attention as ground truth. So there is no one manually annotating the annotation. The system is trained purely to take the image and the question as input and to try to find the correct output. So the correct output is given during training, but it's not given during testing. And then we want to design an architecture that allows to have those attention maps. And this is what our system came up with. So in this case, despite the fact it never saw those attention maps, it wasn't encouraged to come up with those specific attention maps. That's what this system kind of.
Same system you already described?
No, that's a different system now. So I show you the architecture actually, yeah, after the next slide. So classical techniques, what they typically do is they design fairly complicated attention mechanisms. And what we thought was, let's just interpret that as, again, like my background is graphical models, so I have this probabilistic notion in mind. So let's try to come up with some form of probabilistic model here. And so the architecture looks a little bit complicated at the first place, but actually let me break it down for you. It's very easy. There's this bottom part here. And all that bottom part is doing is just extracting image representations or data representations. And so for the image, we typically use a convolutional neural net. And that's fine. You just use some convolutional neural net that comes up with a spatial representation over your pixels. Then for your question, you use some long short-term memory model similar to the ones that I showed in the first part, where you come up with a representation, a temporal representation for each word in the question. And now we take those representations, those data representations, and then we have this attention unit. What it does, it kind of generates those probability maps. And then we are multiplying the probability that it generates with the spatial or temporal representations for the image or the question, respectively. And then we are feeding this attended representation into the decision-making mechanism. So the system is, in a sense, very simple. It consists of three parts: the data representation, the attention mechanism, and the decision-making part. Each of those are some form of neural nets. Again, the whole system is trainable end-to-end. Everything is differentiable. And what I showed you earlier, those plots with attention, are kind of what comes out of those softmax units in the end. In particular, the ones on the image was what came out of what was multiplied with the image representations in the end. And the probabilistic notion is we have those kind of similar to graphical models. We have those unary potentials and pairwise potentials that come in that help us to generate those attention mechanisms.
How does the attention piece compare to some of the other kind of attention models recently proposed by folks in the learning world?
Right, exactly. So you see many of those attention mechanisms, and they are specifically designed for the visual question answering task. And so there is work like on hierarchical co-attention, for example, where they design a fairly complicated attention mechanism where they take the representation mix and match them together and kind of try to encode this implicit notion of iteration, in a sense. And that's kind of what we wanted to get away from. And we want to have like a very simple interpretation of those attention mechanisms.
Is it trained?
This system, yes, we do train this system. So there is the data set that I mentioned earlier, the VQA data set, where there is questions, images, and corresponding answers.
So I thought I've seen models with like an image attention model in the past, basically learning some weights to multiply across the image.
Right, yeah.
Before, right?
Yes. There is baselines, and I think I referenced those. Yes, there is work by Liu and others, and Fukui and others, and they have designed similar mechanisms.
So what is the multimodal part of this? That's what you were talking about.
Right, so the multimodal part is really, we have this kind of unary potentials, then we have those pairwise potentials where we're attending to, kind of jointly attending to multiple inputs. And we actually extended that more recently, that we have, you can take a larger number of input modalities, and then you have like higher order type of models. So it's really this graphical model type of interpretation that we went for in this case. And here are just some results. Again, we never used as input any form of attention. So this is, in a sense, trained in a totally unsupervised manner. And you can see that the system, here is the question is, what color is her dress? Again, a tennis player. I guess there's Roland Garros going on these days. So, we have, in our case, an attention that focuses pretty much on the player as opposed to some of the baselines that look somewhere else. And this one is very focused. Another baseline which is also very focused. Some other example here, one of the other baselines is kind of spread out all over the place and not very much focused on the birds in this case. And there is one where our approach as well as the baselines kind of perform reasonably well. There's also some failure cases, and the interesting part is, where do those systems go wrong? And here's one image. It's kind of hard to see. It's kind of a grayish type of image, and there's one object in there which is the umbrella, and the umbrella is very colorful. So irrespective of whether you're asking what color is the table or what color is the umbrella, the attentions that I'm showing you here all look identical, and they always focus on the umbrella. And it's kind of distracted by the colorful object in the image, which, kind of makes sense. It's like a little kid almost. The colorful part is the interesting part, and everything else is kind of boring. And we see similar things happening here. Now, kind of putting that down in numbers, if we compare to the baselines that I showed, we perform reasonably well. I think by now there is newer numbers out there. There's a lot of people working in that area, so there's papers appearing on arXiv almost every week. So it's, I think right now that we are still pretty good, but I think there's other baselines that work better by now.
So I wonder whether you can train the network in the other direction. Let's say if you have iGaze data, when people are generating questions, and then you feed that data into the network, and then you test the system by feeding into the gaze data, and then the system can generate the sentence by reading this person's mind.
Right, that's a very good suggestion, and we could do something along those lines, and I think that will be something very interesting to do. We have actually been thinking about, can we get some form of gaze or some form of attention and use that as a supervisory signal in those systems. Now, that's why I was very excited seeing some of those eye tracking results yesterday, and I've been very excited to look into some of this data and try those systems with that supervisory signal at hand. I think that would be something very interesting to do and to see what actually happens there.
And just to add to that, I mean, there are certainly data sets you can grab that have, their images, natural images that have been run on a population with an eye tracker, and so you can see the maps where people were looking. There was no context there, no task context, but at least you give us some sense of where the attention went.
Right. Yeah. The data sets that we looked at, for some of those data sets, there was no question there, or there was no answer generated. So we would need to come up with those at this point in time, which I think we should do, and I think that will be very exciting to do. So again, that's why I was very excited to see some of those things yesterday, and I was like, oh yeah, I should get my hands on one of those, and we should try something. So that's exciting. Yeah. Then I'm not sure how I'm doing actually on time.
Maybe like 4 or 5 more minutes.
Okay, I see. So I quickly rush through that. It's a kind of an unsupervised video object segmentation type task. Again, the reason I saw a lot of video data being processed here, and some of the work that we have been looking at could maybe nicely tie in with what you guys are doing. So given an input sequence where we were interested in figuring out what is the main object, that was kind of the first task that we looked at. Now, let me kind of skip through that. The main takeaway from this part probably is similar to what Jim was kind of mentioning yesterday. Here we are leveraging a decent number of cues, spatial connections, temporal connections, non-local connections to generate or to come up with a system that is reasonably robust. And then maybe that's the graphical model part. We are also modeling foreground and background at the same time. So many systems that you see out there, they typically just model the foreground, but they are not so much interested in the background. So different from those techniques, what we did, we modeled both foreground and background at the same time. And then we use a conditional random feed to fuse those results. And doing that, we managed to obtain decent results, I'd say. Now, kind of going forward, since I only have 5 more minutes, the one thing I want to point out, and that's kind of more recent work, is we started to look into segmenting multiple objects on an instance level. So how can we label multiple objects? So it's video instance level segmentation, semi-supervised video, semi-supervised object instance segmentation. So here is one example. Let me see whether this actually works. All right, so here's one of the sites that we're able to generate. So those are short video clips from a data set. And similar to the SegTrack V2 data set that Jim and his group released, there's now a Davis data set, and they actually use some of the data from the SegTrack V2 data set. And so that's kind of the data that we use here. The system, again, it's one of those deep learning systems that we are designing. So the input is, in this case, the current frame and the previous frame. We compute the optical flow. We use the prediction from the previous frame. We use the optical flow to warp it. And then we use both the 3 inputs, the current frame, the optical flow, and the warp segmentation into a neural net. Now, that neural net consists of multiple streams, 1 stream per instance, per object instance. And each of those neural nets predicts 2 things. It predicts the bounding box, and it predicts a binary segmentation map. And after having predicted those, it fuses the bounding box with the segmentation map, and then again fuses all those into a final output prediction, which is then used in a recurrence relation to kind of feed the next frame. So it's again similar to those LSTM type of networks. And again, everything is differentiable, so you can train the entire system end to end. Now, to kind of break those neural net parts down a little more, they consist of 2 neural nets, actually. As I said, the binary segmentation net and the object localization net. And the binary segmentation net consists of what we call 2 streams, an appearance stream and a flow stream. And those are, yes, fairly standard neural nets, I'd say. Now, I know that this was kind of quick, but if we look at an ablation study, we have the segmentation net, the localization net, and the RNN component. And as I said, the segmentation net consists of an appearance stream, a flow stream, and then warping the mask or not warping the mask. And then you can kind of see we enable all those components one by one, and the standard data sets that were, or some of the standard data sets that were released recently, we apply this to, and you can kind of see the more components we enable, the more the performance improves here. Now, we also compared this to a set of baseline approaches here, and we obtain decent performance on this novel task of video object instance segmentation. And again, some of those results, I guess Jim is very familiar with the Penguin data. It's, let me see whether this actually works. Here, they're not moving all too much, which is why this is kind of, maybe I should say that, let me say it's not too difficult for the neural net to kind of pick up that part. What is more difficult, and this is kind of a success and failure case at the same time, is here you can kind of see where things start to go wrong and what we need to look into as the boy bikes along. You can see that whenever there's occlusions, the system is kind of losing losing part of the object track or latching onto something different. And this is something that we still have to work on in order to get more robustness here. But again, the main point being here, this is a task where data hasn't been released until very recently. I think the data came out, the Davis 2017 data came out in March this year, I think. So it's kind of very early results. All right, now, since I'm sure I talked way more than 5 minutes, last part, let me skip through that. Idea is to get more consistency in there. I showed you those autoencoders. We have a unary decoder and a pairwise decoder, so now we make the system somewhat more complicated, a little more complicated by having 2 types of decoders. They feed into a graphical model. The whole system, again, being trainable end to end, and you can just train those systems. Now, if you look at what are the results, on the right-hand side, you see the baseline from Max Welling and our approach, and you can see that if the bottom row is probably the most interesting one, because what we did there was we extracted those representations that are, or those generated images that are furthest away from any sample in the training set. And you can see that for the VAE approach, there is samples that are barely recognizable as faces, as opposed to for the SVAE approach, where even though we really picked the ones that are furthest away from any sample in the training set that were generated, it still looks somewhat like a face. That also manifests itself in some numbers on different data sets where the approach works reasonably well. Sometimes the improvements are fairly minor. If you look at the Toronto face data set, actually you can see that it's almost inconceivable differences. For other data sets like the Verge 7 and Facade, which are discrete data sets, the difference is larger, and that intuitively makes sense because graphical models were more designed for discrete data type of tasks as opposed to continuous prediction tasks like MNIST and TFT. So that kind of seems intuitive as well. All right, let me now wrap up. In conclusion, I think there's many open challenges in this area of trying to get everyone's to exhibit some form of curiosity, but also being creative at the same time. So not only always like predicting the same thing, but generating systems, generating output, envisioning output, and producing, importantly, output that is somewhat consistent. All right, thank you.
We really have time for one question where you
Alex. So let me ask you naive questions. I don't know.
There is no naive questions. Any question is good.
You described these new systems like LSTM for doing the sequential. And then I can imagine using something like deep net, which is given as an output setting. Is the advantage of these systems that it's easily trainable because it's differentiable, or what would be the advantage of this over standard?
Yeah, you're raising a good point here from a mathematical perspective. What the LSTM systems are doing, they're kind of modeling a joint distribution based on a product of conditionals. So P of yt given yt minus 1, yt minus t, and so on and so forth. And then you multiply over all the sequences. As opposed to like graphical model type techniques, where you're trying to model the joint distribution as like a joint distribution with which factorizes, say, into products of unaries and pairwise, for example. And so that's a different paradigm in modeling those systems. And depending on the type of data that you're using, sometimes it's easier to model using the conditionals, and sometimes it's easier to use the joint. Now, for time series data, because everything is backpropagated end to end, it's very easy to go for this conditional type of approach. Now, this is not so much true if you look, for example, at images. If you want to model probability over, say, segmentation masks, what would be the notion of time there, right? You could imagine you go through the image left to right or top to bottom, and there is just no convenient way of how to connect those pixels. Now, that being said, there is people that try those models on this type of, or those approaches on, say, image data. There's papers like they're referring to it as pixel RNN, and which what they're doing there is modeling
using autoregressive models to model image segmentations in very much the same way as I've shown for temporal data. And they are able to produce decent results as well. So it's hard to tell, I guess, what works and what doesn't work. Those approaches, depending on the type of data, you probably can make any of them work.
All right, thanks so much. So to wrap up.